So we're going to be talking about the black magic and the black science of speeds and feeds for the next half an hour, 45 minutes. And I'm really excited about this because I think a lot of you joining probably know Vince primarily from social media. His handle is Vince Fab, and a lot of people refer to Vince as a sort of like Mad Max or the like Maverick of desktop CNCs. He's always able to like take these machines and it feels like push them right to the limit and then like go that one step further, and has just been really a force in this community. So we're super excited to have you with us. And I think also before we jump in, it's worth noting that Vince is now on the team at Saunders Machine Works. I'm sure many of you listening are also familiar with all the great stuff coming out of NYC CNC and John's shop, and lately ProvenCut, which is a website that's devoted to creating speeds and feeds recipes, which is part of the reason why we are here. We sent John and Vince and the team one of the Bantam Tools desktop CNC milling machines, and they have been putting it to the test and developing some of these speeds and feeds recipes to share with you. And as sort of a precursor to that, we wanted to sit down and talk about what this stuff is. So Vince, any other context that I'm missing?
No, it's pretty good.
Before we get into like showing slides and stuff like that, let's give people a moment to get to know you. And how did you get into being this the Mavericks of the desktop CNC world?
Oh, I don't know about the Maverick part, but I'll give you a little background. So I've been a motorsports fabricator for about 20 years, working in pretty much high performance automotive. And the machining part kind of came into play when I lived in Puerto Rico, and we had a little Bally combo mini mill lathe, and I did a lot of manual machining for little parts. And that's kind of where I started to learn, machining, something that I wanted to keep doing. And the more I could machine, the less I had to make stuff by hand, So I was also making a lot of intake manifolds at the time, and some of these were 30 plus pieces that had to, were all hand built and had to be welded together.
And so you're keeping stuff in house, and you were initially relying on desktop CNC machines. I think you had a Shapeoko was maybe your first machine.
Yeah, so I bought a Shapeoko as my first machine to start to kind of keep everything in house, mostly the prototyping. Mm-hmm. I never thought I was going to be doing 3D machining on stuff that I could sell as an actual product, but in the end, that's kind of what happened.
Yeah.
It just with all the fabricating, it seemed like the industry was moving towards more CNC parts and integrating that in, and using the machines as a force multiplier to make better parts more efficient, and that was just the way to go.
Yeah. We've been working with Vince for I think a little over a year now. We had sent Vince. Vince was a Bantam Tools remote resident too, with our little 17-pound Bantam Tools desktop PCB milling machine, and we were just blown away then. And now that you have the new CNC machine, we're just super thrilled. So let's dive in. Here's what we're gonna do. We're going to give you the quick primer on speeds and feeds. If you are new to this space, welcome. I would say, I'm definitely not an expert CNC machinist by any means. I'm, squarely, I would say beginner intermediate user. But we want to give newcomers a little bit of context as to it, because there's lots of tech and lots of lingo in this space, and it's easy to just get overwhelmed with that. So we'll do a quick primer on speeds and feeds, and then I'm going to hand it over to Vince, and he's going to talk a little bit about his process and sort of his workbook, if you will, that he uses to approach speeds and feeds recipes when working with this class of machines. So hang on one second. Let me turn on screen share. Oh, and before I forget, we've got a chat going on the right-hand side. So if you've got a question, definitely drop it in there, and I will keep my eye out. We'll pause along the way. I think the way that this stays fun for us and for you watching is if you ask questions. So yeah, please don't forget to do that. All right. Vince, can you see my screen?
Yes. Good to go.
Okay. All right. Speeds and Feeds 101. Oh, and also, if you are a veteran machinist, you're probably going to hear something in here that you're like, hey, I have a different way to explain that. Or like, we want to hear that. So definitely drop that into the chat as well. Okay, so what are speeds and feeds? So I think about these as kind of like the two of the most important levers, kind of like, levers on a backhoe, right? That you are going to be using to control the parameters of a cut and to really be dialing in a cut on a machine. So feed is relating to how quickly that end mill is going to move through that material, whereas speed is going to be relating to how quickly the cutting edge is going to be moving along that material. Feed is usually in inches per minute. Speed is usually in this thing of SFM, or surface feet per minute. And it gets a little bit confusing really quickly, or a lot confusing really quickly, because when we think about speeds too, a lot of newcomers, and myself included, talk about RPMs, revolutions per minute. How quick is that tool spinning? Well, it's important to think about like the analogy of like, right, tires on a road. So if you've got some crazy bicycle contraption like this, and you've got a small wheel and a big wheel, like the trivia question is like, if you've got a small wheel and a big wheel in a setup like this, and they're traveling for a minute, which wheel went farther? Is it the big wheel or the small wheel? Well, the trick is that they both went the same distance, right? The difference is that small wheel has to rotate faster. So if we bring this back into the machining space, these two equations here, you can find, the internet is littered with SFM and RPM equations. They're directly related to each other, and they're controlled, or I'd say they're correlated through the cutter diameter. So you often find numbers like this, which are these SFM tables. And if you're just getting into CNC, again, you see something like this, you're like, HSS, SFM, what are these things? Well, just remember that SFM, or that surface feet per minute, relates to RPM, and tooling manufacturers typically provide tables like these, or if you're more like old school machinist, you're used to these kind of rule of thumb numbers of surface feet per minute that you're trying to stay within. And again, if we're going to go back to RPM, the faster that spindle is turning, or the larger the diameter, the higher the SFM. Okay, we're gonna keep demystifying this. Okay, so why is this important though? Well, we all have this like beautiful image, right? There's just like this chip stream, and you've got these chips that are coming off. They're all uniform. They're shiny. The heat is leaving the material, in these chips. And this is sort of like perfect world, right? And the reality is that it's more of like this balancing act. You're constantly you're usually getting two out of the three of these things, but not always all three. And so we've got on the sort of edges of this triangle, right? We've got material removal rate, how quickly you can actually machine something, how quick can you make that part. If you're a job shop, right? Time is money. You're focused on this. And the other balance is tool life. Well, if you as we'll find in a minute, if you move too fast, you can actually be burning up a tool or breaking a tool. So how are you preserving that tool life? And then the last thing, Vince's specialty, surface finish. I see Barry has a question in the chat. Will these slides be available after? Yes, they will. Definitely look out for that. Vince, interrupt me where I'm wrong. Also, I see we've got John Saunders in the chat too. So John's really the master of this. John, pipe up if you've got something to share. So we were doing this balancing act, right? But there's this idea of like a sweet spot. I thought this is a great slide. This is in Bob Warfield's CNC cookbook. And I think this kind of cuts to the point, right, of Well, what's going on in this balancing act? So if we look along the bottom of this chart, right, the faster that we move our spindle, we can actually go into this direction where we're going too fast, and our chip load, or how much is coming, how big of a bite each flute on that end mill is taking, could actually get really, really tiny. And you start doing this thing where you're burnishing, you're rubbing, and you're really reducing the tool life. We're going to talk more about this in a minute. On the opposite side, if we go up to the upper left of this chart, you could be feeding too fast too, right? And you can be taking a really, really big bite with every tooth. There, you could actually just snap an end mill. And I encourage you to look at some slow speed high speed photography, slow-mo videos of end mills breaking apart on YouTube. It's some pretty spectacular footage. But the most important thing here, right, are these green boxes. So like, what are the sweet spots? If you're feeding fast and you're spinning fast, you're kind of in this high MRR, upper right territory. And if you're in this kind of middle of the road, you might be optimizing more for surface finish and tool life. Ideally, you've got a good mix of all three of those edges of that triangle that we were looking at back here. But if you're really going to go hard on material removal rate, you're usually going to be sacrificing one of these other parameters, which is why we have things like roughing and finishing, right, Vince?
Yep.
So, all right, we're continuing through this, and we're like, stay with us here. I would say we're 3/4 of the way through our quick Speeds and Feeds 101. So chip load, this is what we were just mentioning. So as that cutter is spinning around and it's moving through the material, it's taking a bite, and the size of that bite is what we refer to as chip load. And as Vince was giving me his primer on how he approaches Speeds and Feeds recipes for these machines, this is definitely a critical number. Usually, Vince, you program with, as a conservative, 1 thou chip per tooth. Is that right?
Depending on the cutter diameter, but usually 1 thou is pretty safe to start off with. Yeah. So that means you're going to get a nice clean chip, and you're not going to be creating any heat, and your chip will be of significant thickness to take that heat from the cut.
So this is what we're talking about. That little flying ember there below the word chip that's our chip, and this is our chip load. Okay, so but again, you're like, all right, so I've got speeds, I've got feeds, I've got chip load, I've got this sort of dance between SFM and RPM. I've got it, right? And then all the other machinists in the chat are going to pipe up and say, no, there's actually like 15 or 30 or 100 other factors that we look at. And the point of this isn't to overwhelm you if you're just looking at this for the first time, but I think is really to just hopefully inspire you that there are some really important things to focus on. And then remember that there are other levers, if you will, that you can continue to dial in, and things that will affect material removal rate, surface finish, tool life. We'll talk a bit more about these as well. Vince, is there anything on here that you're like, oh, actually, they're missing this other? I'm sure there are hundreds of things that are missing, but anything that immediately jumps out at you?
Those hit the pretty important parts. I mean, you can see how much affects your cut. Pretty much everything matters, so I know how that can get pretty intimidating to people who are new.
Yeah. Okay. Last little bit of definitions here. So we've covered speed, we've covered feed, we've covered chip load, axial depth of cut and radial depth of cut. These are also things that you'll come across. And really, these are fancy ways to say the depth of cut or the width of cut, respectively. The radial depth of cut is your width of cut. The axial depth of cut is your step down. It's also referred to. And these are two parameters, right, that are going to dial in how much material you are removing in any given minute. And then the last piece that's really important to these machines is this distinction between conventional cutting and climb cutting. And this really relates to the feed direction in relation to the way that the tool is spinning. For our machine, for the Bantam Tools desktop CNC milling machine, say most of the time, if not all of the time, we're really climb cutting. That's what this machine likes to do. But there are some cases where you might experiment with conventional cutting, and Vince can talk more about that in a second. Okay, that's the quick primer to give everybody some context. There are a ton of great resources on the internet. John Saunders, NYC CNC, has a couple really great videos on speeds and feeds. Haas also has a great explainer video on speeds and feeds. But as we'll see in a minute, part of this is also learning on the job and experience and using your eyes and ears. So, Vince, I think this is what you said to me last night as we were prepping for this.
Yes, this is one major thing right here is pretty much no CNC machine is going to act like another one. You really have to take everything into account. And that'll kind of bring us into with the larger machines. Do you have that slide?
Yep.
So the industrial machine can push thousands of pounds of lateral force, and they usually have super high horsepower spindles compared to a desktop machine, 10, 15 horsepower. But they usually use bigger tooling at a lower RPM, which still means they get their SFM. But once they start going to smaller tooling, it can get a little bit different.
Yeah.
Also, I feel like the manufacturers for end mills really kind of tailor everything to the industrial machines, where the tooling is more the limitation, not how much power your spindle has or how much force you can push on, let's say, your x-axis.
That's a really important point. I think, certainly looking at those tables, like, and if you buy a tool from, Harvey or Helical or Datron or, Lakeshore Carbide, I think to your point, Vince, a lot of those tables and the documentation is really geared towards these large machines. Okay. As opposed to.
All right. I did lose the video. So,
okay.
You can still hear me though?
I can still hear you. Yep.
Okay. So as opposed to a desktop machine where it's much smaller. I mean, most of these are going to be under 100 pounds. They're portable, and they can usually push, depending on their drive system, anywhere between 5 pounds and maybe 100 pounds of force. So you can kind of see where it's different compared to an industrial machine, how we have to go about setting up our speeds and feeds. The spindle speed is also a very important thing. That it kind of changes how we use tooling. I kind of like using single fluid end mills quite a bit with high RPM spindles because it lets you keep a decent chip load while still feeding at a slower rate.
Cool. Let me, Vince, have you lost video for a second?
I'm getting it back.
Okay, cool.
Not the best internet. I'm sorry.
No problem. The other thing that you talk a lot about is this K factor.
Yes. So K factor would be the volume of material that can be removed in 1 minute by 1 horsepower. So K factor I use in my workbook to determine feeds and speeds because it'll tell me the machine force involved in a cut. And some of these machines are so, I guess, sensitive. Even a half a pound of force matters, difference in a cut. So it's something that I use quite a bit. And I'm not sure if you use something like that in a larger machine. I've never programmed an industrial machine, but I wouldn't think they care.
Right. They're just gonna spit out the power.
Yeah.
Okay. So before we switch over, last slide of this deck, before we switch back over to video, is your workbook, which we thought about showing you how to run through this, and there's a lot of stuff on here. So I think we're going to provide a download link to this. But Vince, maybe you can call out like why you use this workbook, and then we go into a little bit about your process and look at some of the parts you're working on.
Okay. Well, this workbook, you pretty much, it allows you to center upon different factors. I like to base speeds and feeds off of a minimum chip load when I start, and it lets me input my tool specifications, my RPM, the chip load that I want, and then it tells me what kind of feed that I should be feeding at to get that minimum chip load. Then I input my axial and radial depth of cut. And I think this is where a lot of the desktop people kind of use just trial and error. But The K factor allows me to see how much force is in a cut, and that changes with your axial and radial depths. Desktop machines are not super rigid. They're not known to be very rigid. So usually I like to take a smaller axial depth of cut and a larger step over. It works pretty well.
So you start with the machine force per axis, which is our rightmost arrow, or do you start on the left side of this chart?
All right. Well, so I don't see the chart. It's actually not coming up on mine, but
okay.
So I'll just kind of
you'll wing it, and I'll point to where we are.
Okay. So I'll start by inputting the end mill specifications on the upper
left-hand side,
upper left, and then what kind of chip load I want. And usually, like I said, I'll start at about 1 thou. For 1/8 and 1/4 inch tooling, 16th and smaller usually gets quite a bit smaller, about 5/10, and some of the Harvey micro stuff calls out for, I think, 2/10 chip load.
Whoa.
Yeah, so those are the fun ones to run. But because I have the K factor, I know how much force is in the cut, and the worksheet actually shows me deflection as well. It's pretty easy to get a clean, reliable cut on the first try. It may not be the one that removes the most material or has the best surface finish, but you usually won't break a tool on the first try.
Yeah.
So it'll be a successful cut. Reliable.
Okay. So you're inputting the tool parameters on the left-hand side. Then you're jumping into inputting the maximum acceptable deflection, which is right to the below and right of the left-handmost arrow. And then you're looking at machine force. Now walk us through the right side of this chart.
Okay, so is this where you put in the axial and radial depth of cuts?
Yeah, and the machine force and stuff.
Okay, so I'll start, if I haven't used a machine before, by seeing the maximum machine force that an axis can put out before it skips. It just kind of gives me an idea of where, my sweet spot bubble, is going to be. And so below that, I'll start inputting axial and radial depths of cut. And the way I do that is usually I'll start really, really conservative on especially an axial depth of cut, because that's never going to hurt you. If you are very conservative on radial depth of cut, you have to start thinking about chip thinning. I know we talked about that a little bit.
We actually didn't touch on it, and so maybe we should let me go back just a few slides, because I think that this is important to touch on for a second. And I think this is part of a Speeds and Feeds live stream number 2. But the chip thing, it's honestly it's less of a concern most with roughing on our machine, because most of the time we're taking larger than 50% tool diameter cuts. But where chip thinning comes into play is if we look for top down, looking at this tool here, this 4-flute tool, if the radial cut or the step over is less than 50% of the tool's diameter, meaning you're just kind of following along the edge, then you get this thing called you have to consider chip thinning. So Vince, what is chip thinning?
So chip thinning, like I said, like you said, occurs under 50%. It's where the thickness of the chip is less than what your calculator would tell you. So I don't know.
You can't rely on these. You can't rely on the equations basically to be accurate.
Yeah, especially so even in like Fusion, if you're doing adaptive and you want to take a very small radial depth of cut, you kind of have to do the equation yourself. It doesn't take it into account.
Cool. Okay, so we'll go back over to the spreadsheet for a minute, and then we're going to look at some parts. So you've input your depth of cut and width of cut, which is the second arrow to the right. Typically, with the Bantam Tools desktop CNC milling machine, we're doing a much larger width of cut than we are a depth cut. The general recipe that we like to run for like a 3-flute flat end mill or one of the Datron single flute tools is around the order of 200 thou step over width of cut and somewhere between 18 and 20 thou step down. And so that's a think about where you're landing with these recipes too, right?
Just about. I think I went a little bit less than the step down just to be conservative. Just because with desktop machines this size, the step down has a pretty big effect on the health of the cut. You'll start to hear chatter and everything on very small differences.
Right.
So that's why it's better to kind of take a conventional approach to cutting, but use constant load tool paths like the Fusion Adaptive, to where you don't get any kind of spikes in your machining. If you can keep your load constant as possible, you'll get the best surface finish and the best cut.
Yeah. Cool. All right. I'm going to hop off of screen share here, jump back over. Let's pause for a minute and look at some of these questions in chat. And also we realized about halfway through there that chat had been disabled. So we're going to pause here for a minute. Vince is going to do some show and tell. Chat should be back on now for everybody. So if you've got a question, please jump in and ask it. Vince, so you start with this calculator. Now walk us through the next step. What are you doing? And if you could show some parts too, that would be really awesome.
Okay. The next step is pretty much when you make a cut, you want to listen to it and you want to see, the marks left behind. So you still have to kind of use your senses to really, really narrow down that sweet spot. Did you want to talk about chatter at all?
Yeah, let's talk about chatter and what do you mean when you say look at the marks on the surface? Like, what are the telltale signs that you're in the zone, you're in that sweet spot?
Well, you're pretty much looking or listening for irregularity, spiking or just vibration that you can actually hear, and you can see pretty much everything in your surface finish. And that's actually one good reason to have a low axial depth of cut and a larger step over, because you'll be able to see quite a bit more of kind of how that tool is acting as it's cutting. So there's a lot of people that run adaptive and run a very low step over, and you can't see any kind of real floor finish. So you have to base everything off kind of what you listen to and what the chips look like.
Right. So because you're, just to sort of restate that again, so because you're taking that really wide cut, you're using most of the tool, you can look at the floor of the part. Maybe you can hold up the one of the test parts that you have. You could look at the floor and just try and identify where the tool might be bouncing around on the surface.
So can you see that? Yeah,
we can see that. Yeah. So what were you, so this is a test part that you were working on. What were you kind of working through, and was there anything in those 4 different parts that you were changing up, or was a surprise to you? Or
well, the nice part about programming this is I use the plan setup. So I was able to do the cam on pretty much one part and then move it over with the plan instead of re-entering a program every single time.
This is the plan setup in the Bantam Tools software.
Yes, it is in the software.
Cool.
What I really tried to figure out on this is, surface finish, because it's a aesthetic part. The boring, try to get that right, because when you bore small holes that are close to your end mill diameter, things start to get kind of tricky. And the contouring, which is a sidewall finish, it's kind of hard to tell, but each one of these little pockets, was pretty much a different recipe trying to get the contour to have the nicest surface finish.
Hey, Vince, we got a question in here about the impact of active cooling, which, Steven, I'm pretty sure you're referring to like flood coolant, like the actual flood coolant liquid that we see coming out of on more industrial CNC machines. But Vince, do you want to take that one?
Yeah, sure. I've kind of done it all. I started cutting with WD-40 because I didn't know anything about speeds and feeds, and it kind of let me push the boundaries a little bit, even though I didn't have anything right. And after that, after kind of learning what I was supposed to do, I started using an alcohol MQL system, which is a minimum quantity lubricant, which is alcohol and water I mixed so it wasn't flammable. And something like that works quite a bit, like pretty well. If you're really pushing the MRR, you're putting a lot of heat in the material, and you need to make sure it's not building up. So right now, because I've pretty much been machining at home and I don't want an air compressor running the whole time, I cut almost exclusively dry.
Yeah, I was gonna say, and that's pretty much like, so this machine in particular, it's kind of designed to be sort of pushing the boundary of what you can do dry machining. But the impact of like flood coolant in a larger CNC machine is that you can run faster. You don't have to worry about your tools burning up potentially as quickly, right? Your chips are getting out of the way.
Yeah, definitely chip evacuation is a very big thing in these desktop machines. So it can help, but I wouldn't say it's a necessity to run active cooling.
Yeah. Michael's asking, is this machine able to do helix boring? Yeah, any helical entry for sure. Right, it reads any G-code file. So yes, helixing is the way to go. And actually, that's another kind of speeds and feeds or maybe we can use this as a segue to talk about playing to a machine's strengths. So if you're in Fusion 360 as your CAD to CAM workflow, which is definitely something we recommend, there's this thing called helical entry angle, and that's usually how quickly that tool is going to helix down into the material. On a much stronger machine, where you can do like several degrees. On this machine, we tend to do like 1 degree or even like 3/4 of a degree. Vince, what did you find? And maybe you can talk a little bit about that.
Well, I think, like I said, the boring is a little harder just because you have to get all those chips out of the way. So I find a single fluid end mill is usually the best way to do it if chip evacuation is going to be an issue. I don't use the angle like you do. I usually do an amount per revolution, and then adjust my feeds and speeds based on a video that Haas put out about speeds and feeds that were wrong. So it's a little calculator because I guess the feed is based on the middle of the end mill. So if the hole is small, you have to adjust it because it's the outside of the flutes that are contacting.
Okay, so we've talked about you're using, so like when you made that first part, you're looking at the floor finish to see if there's any noticeable chatter. Let's talk about chatter maybe for a minute. Like what are the good sounds and what are the bad sounds? Do you want me to play this video too? You can kind of talk over that.
Maybe. Well, I don't. There is actually a little bit of chatter in that video.
Sorry. Yeah, I didn't mean to say, hey, let me play this video where there's tons of chatter. No, I meant let's talk about chatter first. Yeah.
Yeah. So I've heard people, both ways. Some people very adamant about chatter is always not acceptable. But the thing is, on a desktop machine, it happens. You just kind of have to manage it, especially if you're pushing your MRR, you want to move a lot of material. Maybe you already have a roughing tool that's beat up a little bit. It's okay to have a little bit of chatter as long as you don't kind of push the limits to where you get deflection that's going to change anything about your finish in the final part. So chatter does happen, and I think it's all the way about how to manage it with the desktop machines.
How do you manage it with the desktop machines?
You have to leave a good amount of stock to leave, radial and axial. There's we've talked about a little bit about wall contour where I won't just go from a rough to a finish. There'll be a rough, a semi-finish, and then a finish. And that's because, the first one might have a little bit of chatter. It's you need a pass that's going to be that's going to have the same kind of force on it. That's why I do a semi and then a final. But
a semi finish pass and then a final finish pass.
Yeah.
Yeah, and I think that this is we'll cover this in again. I'm going to just start referring to the speeds and feeds live stream number 2 because there's this whole other bucket of this stuff is really dependent on the type of cut that you're doing, roughing versus finishing. So, sorry to interrupt. Keep going.
All right, where do I start? There's just so much because everything matters.
Yeah. Everything matters. Let's look at this video. Maybe you can just talk about some of these setups, because recently you did try and really dial in a bunch of things making this mold part, right?
Yes.
Which you have there.
It's kind of hard to see, but it was an exercise in just kind of surface finish, because that's important for something like this. And there was a couple things that I wanted to try on that part that were pretty fun. A peck drilling with a 1/4 inch single flute end mill. So this right here is facing with a Datron 12 millimeter two flute, which is one of my favorite tools. And right here is a 6 millimeter Datron single flute.
I'm gonna just for 1 second go back here. Okay.
All right. So yeah, this is the finish from a facing operation with the 12 millimeter Datron single flute, and I was able to run it both ways, climb and conventional, and as you can see, the finish is nice and very consistent. So that says something about the machine and how rigid its motion system is. So,
okay.
All right. So here we're running a 6 millimeter Datron at 28,000 RPM, and I believe a little conservative at 3.5 thou per tooth.
Okay. Yeah, and if we were to refer back to that worksheet, right, the bigger chip load, the more material removal, we've definitely run that same tool at 5 thou chip per tooth, and but yeah, it's probably good to be a little bit more conservative with it.
Yeah, 5 thou is pretty good.
So this is your peck drilling operation.
Yeah, so if you go back to the peck drilling, so that was just a single flute, 1/4 inch end mill, and I just ran it in, I think 20 thou at a time, just because you don't want to. I couldn't do a boring operation because it was a 1/4 inch hole and with a 1/4 inch tool, and the reason I did that is because I didn't have a small enough tool to interpolate it. But
okay.
Yeah, end mills make horrible drills, so it was a very good test.
And so with this, you programmed this peck drilling operation, which you can barely kind of see in the upper left-hand corner of this video. This end mill is just kind of coming down, removing a little bit, and then it's retracting up and then dropping back down, right?
Yeah. So it doesn't sound the best, but I just wanted to see if the machine could do it. And I think I was able to get the hole within 5 thou, which is not bad. I mean, especially for something that was so close.
Got you.
So you want to go
and then you
look on these?
Switched over to some smaller tooling.
Yes. The first one is a 1.5 millimeter Datron single flute.
Okay.
And I believe I was running about a 70% step over on that, which is pretty kind of hairy on a tool that small. But with the little workbook and the K factor, it was easy to tell I wasn't going to be pushing the tool with this too much force.
Gotcha. Oh. Sorry, folks, having a little bit of an issue pausing and playing this video a bunch. Okay, we'll get towards the end of this. I think we're almost through it.
All right, so right there, this is a little 20 thou Harvey 3 flute.
20 thousandths of an inch, this end mill. So this is
tiny.
super tiny tool. Okay. And maybe if you can just say something about that, like if you're running this too hard, what's the risk? What's going to happen?
Oh, it's just going to break right off. Okay. So these small tools, I mean, if you look at them wrong, it just seems like they're just going to break.
One question that we have too that comes up a lot is folks will be running some of these smaller tools and they'll chip weld. Almost it's in and I can say personally with our new machine, really experimenting with speeds and feeds for the first time on a new part, almost the 1/8 inch tooling is somehow harder occasionally to dial in compared to the larger 1/4 inch tooling. I'm not sure if you've had this same experience, but this is definitely a common question that we get is like, what just happened? My tool just welded.
Well, usually with a smaller tooling, you'll have to take a smaller chip. It's not as strong. So
Hmm.
you'll get kind of closer to that minimum. And sometimes with a smaller tooling, you'll have runout issues depending on what kind of
Hmm.
cullets you use. And
Hmm.
it's a good idea to check your runout on the smaller stuff before you run it, uh, because you could have chip loads from one tooth that are drastically different than a tooth on the other side because of the actual runout.
Got you.
So
All right. So
that's
we're
usually
getting
what
through this.
happens. All right.
And then at the end here, using an engraving tool.
Can you say that one more time?
Is this an engraver that you're using here?
Oh yeah, that's actually a just a 90-degree, I guess, single flute is what you'd call it.
Cool.
So it's a little more cut on one side, and I believe the Bantam engraving is only about 3,000 steep. So,
Okay.
and I'd actually put a
Pretty.
little bit of oil on the top just to make sure it was a nice clean cut.
Can you hold the part up again?
Yes.
Okay.
So
So this
ooh,
is meant to be. Oh yeah, there you go.
yeah.
So this is meant to be like and you did this funny thing that you posted online where you got these two surfaces so flat that putting just a drop of water on them actually made them just friction fit and want to suck themselves together.
Yeah, so apparently that's called ringability, I believe. When you ring,
Okay.
two things together, that
Oh
usually
yeah.
happens with I guess gauge sets because they're nice and precision and flat.
Yep.
So
So
this
takeaway is
yeah,
go ahead. Go
takeaway
ahead.
is with the Datron tooling and this machine, you can definitely get things pretty flat. So I was very impressed, and that's probably one of the best surface finishes I've had on a desktop machine. So, but I haven't tried that
Um,
tool on other ones.
the 12 millimeter tool. Yeah,
Yes.
it's a fun one. So yeah,
Yeah.
it's a stepped two flute and mill. It's really cool. We carry that one in the store. That's one of my favorite tools to run on this machine too. So I want to just cover maybe a couple common challenges that people have, and then we can. Uh, Someone says, "I love the sled and the slim vise setup." Yeah, shout out to Sauner's Machine Works there.
It's the fixture tooling plate and the mod vices definitely work together very well. So I think all the machines I have fixture plates on them. Um, Ease of work holding is really, really high on my list.
Mm-hmm. Yeah, it's something that we're going to be focusing a lot more on too. So common things that you can run into with this, right? Chattering and breaking a tool, chattering and like welding a tool.
Mm.
Um, do you want to talk a little bit about this and some things that like if you were to weld a tool, what would you do in that case? How would you work? How would you move forward? How would you sort of demystify what happened? Because some people will have this and it'll just happen over and over and over again. And
Mm.
what we want to encourage people to do is to like be able to pause for a moment, think about what happened, go back to those levers. Yeah. So how would you work through the welding a tool moment?
Well, I would definitely hit the emergency stop, pretty quick on that one, and then see, double check my feeds and speeds and make sure I didn't fat finger something. I know on Fusion there's quite a few entries, so if you get something wrong, it can do some funny stuff. But the biggest thing is understanding, what went wrong,
Mm.
where the thing, the hiccup happened, and a lot of times in desktop machines, something like chip welding is a cause of not having good enough chip evacuation, and that's a big thing when machining dry. You know, no airflow, no evacuation. But usually single flutes and running single flutes compared to something like a three flute really solves chip welding because you can also run a higher chip load and use less spindle power at the same time with a single flute and mill.
Mm-hmm.
And that's the
Mm-hmm.
whole conversation is flutes and types of cuts and all kinds of stuff like that.
Mm-hmm.
But if you do chip weld and you catch it soon enough, you can actually use a little bit of drain cleaner and give it a little spa bath, and it'll actually dissolve all the aluminum built up. And sometimes you can reuse your end mill if you catch it fast enough.
Yeah, I think that's something to call out, right? Is that some people will like knock a chip out because it welds to the tool. And I can try and pull up a couple of videos, but if you just Google, chip welding, there's going to be 100 videos of people showing this off. But the mistake that people make sometimes too, right, is that they're like, oh, I'll just knock it out of the way. But once that aluminum starts to deposit to the tool, it just kind of gets worse and worse and worse, right? It never usually like fully recovers.
Yeah, it's kind of sad to see too. I mean, especially if you don't know what's going on. You're like, I gotta buy another tool, or hope you have a backup. So, yeah. But usually there's a reason. I don't think I've ever had a tool chip weld and then another one not chip weld. Usually there's a reason. And I see something about thread milling on the side.
Yeah. We actually just did so this is going to be another Bantam shout out to Sean Saunders Machine Works here. We did a video not too long ago that we were sort of calling the like cliff notes to John's approach to thread milling. This machine doesn't support rigid tapping, but you can use a thread mill. And there's some complicated math that actually, if you use John's approach, gets not so complicated. So check out maybe the short video on it and then dive in deeper with John's video. Both of those are on our social page, and maybe one of us from our team can drop some links into those two things as well. Someone also asked, what's the hardest material you've cut on the Bantam? Vince, I think we should just talk openly about this. And I can make the disclaimer. So I'm not sure if we lost your video. Can you still hear us? Okay, we may have momentarily lost Vince. Hopefully he's going to come back once bandwidth resumes. But so the hardest material that we've definitely cut on this machine is tool steel. The machine is billed as being optimized for aluminum, and technically, if you read your warranty for this machine, you are voiding the warranty if you go forth and start machining steels. And there's a couple important reasons for this, and mostly due to the spindle speed and the fact that this is a dry machining operation. It is possible. The machine has the ability. The machine is powerful enough, but it's technically not a supported material. So read your when you get a machine, read that warranty a little bit more carefully. But Vince has definitely done it with using his calculator. But again, it's not something that we recommend. This is not the machine to do steel with every day, all day. All right, Vince, you're back.
Yeah, so I came back to hear steel.
yeah. Well, someone asked what the hardest material is. So Robert, yes, the machine is optimized for aluminum, 6061, 7075. Once you get into some of the harder materials, though, you are going to be kind of pushing the limit of this machine. But Vince, I gave the disclaimer. We don't have your video. I'm not sure if you can click that video button and come back.
Oh, okay.
There we go.
Good? All right.
Yep.
Yeah, so my problem is I use this laptop by the machines, and there's kind of some chips in there. I'm pretty sure screwing stuff up. So it's probably time for a new laptop.
Well, yes, we were just covering hardest materials, and I gave a disclaimer on your machining steel and really relying on the calculator and taking it slow and steady and dialing things in. It's not about really the power of the tool so much as it is in the thinking and approaching the cut in the right way.
Yeah, and really just understanding what's going on, and if you change one parameter, you know how it's going to affect everything else. So yeah. That's pretty much the most important thing. Just understanding instead of taking hey, just go this percentage, you'll be fine. Yeah.
Will is asking a great question. Will Vince's calculator be shared? Yes, it will. We're going to put up a blog post. This is someone from the Carbide community has created this calculator. So we'll put up a blog post with a recap of today's video, and we'll email it to everybody who's been joining us today, along with the slides. The second part of this question I can answer, and then you should explain, Vince. So how are you calculating the maximum machine force and load? So that's kind of a number given from the manufacturer, right? Like you would say, hey, Zach, what's the maximum machine force on every given axis for your tool that I can then input into this calculator? Or is that not how it works?
Pretty much the weakest one. And then I would kind of start from there. So that would tell me a little bit better what the machine can do. And then once I start cutting more and more with the machine, you can come up with a conclusion like, hey, for roughing in this tool, this machine really likes, 4.5 pounds.
Yep.
And then I will adjust that in the worksheet, the workbook, to reflect that. And it'll tell you what percentage of your maximum force that your cut will have. So, and this isn't my workbook. I didn't write it. So some people much smarter than I, engineers. But it's fun to use. Definitely tells you everything. If you like buttons, it's a great workbook to have, and just 30 things to input if you want to know everything about everything.
And Robert's asking about if there's a Bantam forum like a Fusion forums. Not yet, but stay tuned. We are working on putting something together, and there is I should say that there are a few blog posts and live streams that we've done with the Fusion team on CAD CAM. So Robert, definitely check those out. And I think the last word I'll say on this is, so we've talked about calculators and dialing in all these settings and all these levers or metaphorical levers. Just kind of going back and doing another shout out to ProvenCut with this, and also something that the Bantam team is working really hard on. If I were to crack open the door, you could hear machines whining away out there, because we're running these machines 10 hours a day, developing these recipes so that these are things that you can use as a benchmark to get started with. The importance of really trying to soak in some of the speeds and feeds knowledge and have it be able to build some intuition is so that you can go to an awesome site like ProvenCut or go to the Bantam Tools website and pull up a speed and feed and have a starting point, but then have an intuition for how to adjust from there. And I think, at least for me, that's what I'm always looking for when I'm talking with someone like Vince, trying to pick up a little bit of that, I don't know, the machining karate that you do. So
I don't know about that. There's a lot of trial and error. There's a lot of bad cuts, but the thing is when you...
Yeah, but...
Sorry, go ahead.
No, go ahead. No, go ahead.
Oh, so even with the bad cuts, if you kind of use the way I approach speeds and feeds, usually won't harm your tools. You'll hear a bad cut, or you'll see a bad cut, and you can stop it and then adjust, and then kind of see maybe I should, dial down the force a little bit, or stick my end mill up because my deflection's too much, and see where the issue is.
Change your depth of cut. Yeah.
Yeah.
Cool.
But I missed the thread milling part. So, sorry.
Oh, before when you dropped out?
Yeah.
We didn't show any thread milling videos. Should we go out on that? Here, I'll pull up a thread milling video.
It's probably the most interesting, I guess, tool path and way to make nice parts. There's just something about pulling off a threaded part that you didn't have to hand tap, and get WD-40 everywhere and stuff like that. But I recently just got a couple thread mills in from Lakeshore Carbide that I will be running in the Bantam's desktop machine pretty soon. So.
Okay, so as a non sequitur, or as a, not to confuse everybody, but since it was a question, we'll drop in. Here's our Cliff's notes of thread milling that we can go out on here.
The boring.
In this brief
really
overview, we'll walk you through the steps needed to machine threads into your part. And before we go any further, huge shout out to NYC CNC and John Saunders, who have several in-depth videos on this topic. You can find links to them in the description below. In order to set up the cam for thread milling, you'll need two important numbers. The thread pitch, which is straightforward and you'll take right from the fastener that you're using. In this case, it's an M8 by 1.25 millimeter, so 1.25 millimeters is our pitch. The other number is our pitch diameter offset. Every machine screw has a major and minor diameter, marking the respective crest and root of the threads. The reason why you can't just blindly input these numbers is because the tools we use for
Basically,
thread
there's a
milling
lot of
don't
math
always
and
come to a
important
fine
stuff,
point. They're
check out one
rounded
of these
off.
calculators.
The calculator takes this into account and spits back out a pitch diameter offset. Again, more info on this in John's video. So here are the Cliff's notes to thread milling using the NYC CNC spreadsheet. Download the thread milling calculator from NYC CNC. On the second tab, there's a simple calculator for internal threads. Model your hole in Fusion and add the threads to the model using the thread tool and select the appropriate size. Fusion will then model the hole according to the minor diameter. Enter the major and minor diameters into the calculator. Major is our given number, 8 millimeters. Minor is also a number given from Fusion. Now enter the thread mill diameter, which can be found on the manufacturer's website, along with the flat or crest. We're actually going to use a double angle shunt cutter from Harvey that's ground to a fine point, but there will still be some flat, so we're entering 1/1000th of an inch to start. Finally, we'll add thread mill toolpath, select our tool, apply our speeds and feeds, and enter those two important numbers, thread pitch and the pitch diameter offset from the calculator. If at first the thread is too tight, you can increase that offset number by a couple thousandths of an inch at a time until your threads fit perfectly. Happy threading, and be sure to check out John's video for more of an in-depth explanation.
So it's all possible, but yeah, take your time. So Vince, thank you so much again for joining us, and yeah, we will stay tuned, folks, for round 2 of Speeds and Feeds, and yeah, more soon. Vince, any final words?
Thanks for having me, and I hope I didn't complicate anything. I don't know. I could talk about this stuff for hours, and it's just it's so fun to see how everything works together. And then when you start making just beautiful parts that cut exactly how you want to cut on the machine, it's just no other feeling like it.
Yeah. So look out for the blog post and recap. Ooh, yeah.
That's some little 3D right there. So
awesome. Yeah, look out for an email with a link to the blog post that we'll put up in the next day. And there'll be a link to that calculator as well. You can start messing around with that. And yeah, more soon. Thanks, Vince. Stay safe, everybody.